Here we present our solution for the few-shot recognition challenge from several aspects. We will show our method and rough experiments to you. First, let me introduce our team members. Our team is led by Jun Yu, who is an associate professor in the University of Science and Technology of China. He has worked on computer vision for many years and published lots of papers in international conferences and journals. We also have 3 members from Professor Yu's lab. They are Bingyuan Zhang, Renda Li, Renjia Liu. The right side lists our collaborators from NetEase. They provide technology support and computation for us. Their names are Han Yan, Jiaheng Qi, Sudong Shen and Runs Wu. Few-shot object recognition is a long-stand challenge in the field of computer science, which aims at alleviating the problem of data-hungry traits for deep learning. The common categories of few-shots recognition task are zero-shot, one-shot and few-shot. We call them N-way K-shot in a unified manner. For this contest, we could apply few-shot recognition technology to teachable object recognizer, helping blind people to identify the things that they can't see by using a mobile phone. The dataset we used here is Orbit. The Orbit benchmark dataset is a collection of 3,822 videos of 486 objects recorded by 77 blind/low vision people on their mobile phones. 44 people are responsible for training dataset. 17 people for test, 6 people for validation. Here we give some images from this dataset. This dataset is different from other dataset in many aspects. Like videos, random way/shot, blind collectors. But one of the most significant discrepancy is high variation. It includes unbalanced classes, light variation, background variation, viewpoint variation, ill-framed objects, blur. Our baseline method is prototypical networks, which is a method based on metric learning. Its basic idea is that we could learn a prototype or center in latent space for each class using support dataset. Once we have a new query image, we calculate its latent representation and compare it with all prototypes. The label of the nearest prototype is assigned to this query image. For efficient memory, we adopt light to train prototypical networks. That means only partial support images have backpropagation process. As illustrated in the right figure, the red dashed line show the backpropagation. Based on prototypical networks, we utilize more powerful backbones in it. Here are backbone we used. The top left is EVA, it pre-trained model with masked images to regress clip vision feature. The top right is ConnextV2, which proposes a fully convolutional masked autoencoder. The bottom left is EVA2, which use more advanced model architecture. The last is BEITV2, which encode the image as discrete latent space. We inference the query image with all backbones and adopt the prediction with the highest score. For training, we also assemble some tricks. Here we list some of them. They are label smoothing warm-up, cosine LR scheduler, grid search, TTA, dataset balance, sync-BN, grad accumulation, augmentation. In augmentation item, we adopt color jitter, random crop and horizontal flip. We show some visualization for them. Each of them has contribution to the final performance. The last part is experiments. We train each model on the Orbit dataset many times and we choose the best as the final model with fixed parameters. After that we get 4 different meta-classifier-based prototypical networks. And we also adopt the predicetin with higher probability as the final label for the query image. Here display the performance of different model in distinct test data. What we can see is each model has a unique bias, each model prefers some specific test data. We can fuse them as the final result. Thanks.